Now we come to the idea that is at the heart of statics and strength of materials, the idea of equilibrium. This is one of Newton's 3 laws of motion, the idea of equilibrium, and it says, for every action there is an equal and opposite reaction. This is an excerpt from a book that I'm quite fond of. The author was a crusty engineer in Britain. He wrote this book in, I think, 1988, but it stayed in print because it's real popular. And this book is Structures, or Why Things Don't Fall Down. He's got another book that's called Strength of Materials, or Why You Don't Fall Through the Floor. So what he says here is, if a material or a structure is to resist a load, it can only do so by pushing back at it with an equal and opposite force. If your feet push down on the floor must push up on your feet. If a cathedral pushes down on its foundations, the foundations must push up on the cathedral. This is implicit in Newton's 3rd law of motion, which, it will be remembered, is about action and reaction being equal and opposite. In other words, a force cannot just get lost. Always and whatever happens, every force must be balanced and reacted by another equal and opposite force at every point throughout a structure. This is true for any kind of structure, however small and simple, or however large and complicated it may be. It is true not only for floors and cathedrals, but also for bridges and airplanes and balloons and furniture and lions and tigers and cabbages and earthworms. If this condition is not fulfilled, that is to say, if all the forces are not in equilibrium or balance with each other, then either the structure will break, or else the whole affair will just take off like a rocket and end up somewhere in outer space. So when we are thinking about statics, which is what we are studying in this class, statics is the action of outside forces on rigid bodies, we're pretending they're not elastic, that are not moving. They are static. They are not moving. So it's like the foundation of a building or the wall in a building. It is not moving. And why are they not moving? Because they are in equilibrium. And the way you know it is in equilibrium is it is not moving. So here are our 2 friends on a teeter-totter, and because their moments are equal and opposite, that teeter-totter is not moving. Here are 2 people who are not equal, they're not in equilibrium, and so the thing starts to turn. In equilibrium, not in equilibrium. Equilibrium comes from 2 Latin words, equa, which means equal, and libra, which means a balance or a scale, you know, like one of these things. And you see this kind of equal balancing in tower cranes that are used in construction. Here's one over by Olive, what is that street? 13th and Olive. So the crane will be lifting a heavy load on one end, and to make an equal and opposite balance, they will put a big chunk of concrete or something else that's real heavy on the other end. And notice the different distances, the different lengths of moment arms, but they are equal and opposite, and the whole thing stays in balance. Okay, so if you've got a thing in equilibrium, which means it's not moving, if it's in equilibrium, then all of the forces in any direction have to add up to 0. And you could write this as a mathematical equation, and it would look like this. The sum of all forces equals 0. And this zigzaggy thing is the Greek letter sigma, that's a capital sigma, and it stands for sum of. Also, if it's in equilibrium, the sum of all the moments have to equal 0. And you can write that formula like this. The sum of all moments equals 0. So that takes us to your toolbox. These are the 3 equilibrium equations. These are the tools in your toolbox when you are figuring out beams and columns and all that kind of stuff. Now, forces have to add up to 0. They have to be equal and opposite no matter what direction they're going in. But in engineering, we often boil them down to the x components and the y components, because those are just easier. They are straight horizontal or straight vertical, and we can figure them out with CAD or with trig, as you have been doing already. So these are what we call the 3 equilibrium equations. They say the sum of all forces in the x direction add up to 0. The sum of all forces in the y direction add up to 0. And the sum of all moments add up to 0. Well, let's go back to our little kids pulling the wagon. You'll remember from the first week, our little kids had hooked up a couple of ropes on the front end and had wound up resulting in a pull of 14.14 pounds straight ahead. Well, if another kid hooks up a rope to the back and pulls with 14.14 pounds in that direction, all those forces in the x direction add up to 0. And what is the result? What is the net effect on that wagon? It is not moving. And you can picture the kids pulling forward and the kid pulling backwards and the wagon just frozen in space there, because it's in equilibrium. Here are some college students at the University of Washington. They were having a tug-of-war game, and at the moment I came by and took these pictures, they were all pulling real hard, but nobody was moving, which is why I took their picture. And what that means is that the sum of all forces in the x direction were adding up to 0. So nothing was moving. They were in equilibrium. Here's a picture of that out of our book, where he shows people playing tug-of-war, and what we've got are all these forces pulling in the x direction, some of them positive, some of them negative. They're adding up to 0. Here's my friend the spider. I call her Shirley. And she's hanging from a single web. Now, that's a picture of her. You could draw a free body diagram of her. Here's a diagram. Here's the weight of the spider going down, and there is an equal and opposite reaction in the web, tension pulling up. If you wanted to figure out, okay, well, is it the same tension all the way along? Yes, it is, and theoretically you could demonstrate that. Here's somebody pulling horizontally with a rope. Here's a weight pulling vertically. This is like, I don't know if you have these on the Filbert farm where I grew up. We had a big old brass one of these, and we used that for weighing sacks of filberts. And if you were to cut the weight and move that scale to a different point along the rope, cut the rope and move the scale to a different point along the rope, it would still be registering the same amount of pull wherever you put it. Maybe this longer rope is easier. You would find the same amount of tension in that rope no matter where you put the scale, theoretically speaking. So for every action, there is an equal and opposite reaction. If you weigh 140 pounds and you are standing on the floor is pushing back with exactly 140 pounds of reaction. And that's why you don't fall through the floor. We're going to look at that in more detail next term. We'll find out how is it that the floor pushes back. Turns out it's elasticity. It's like little molecular springs. You can draw a free body diagram of you standing on the floor or a beam with a load on it. Here's the load. Here are the equal and opposite reactions, and it doesn't matter which one you label as the force and which one you label as the reaction. We often make the pushing up ones the reaction, but it doesn't matter. And notice I've put this equation here. Sum of all forces in the y direction add up to 0. Here's a building. Pushing down on the soil is pushing up with exactly the same force because it's in equilibrium. If the soil did not have enough bearing capacity and the building were heavier than it could hold up, the building would sink, so it's not in equilibrium. And if a miracle happened and by some chance the soil had greater reaction than the weight of the building, well, you would have a flying building. The building would levitate up into the air. You can demonstrate this equal and opposite reaction with two kitchen scales. Use a book for a beam. Use a can of soup for a weight, for a load. If you center the load and you look at the scales, you'll notice they're reading an equal reaction. And if this thing weighed 10 pounds, you would be seeing 5 pounds on each scale, wouldn't you? Well, you can also put the thing off center, and now you still have an equal and opposite reaction pushing back up. It's just that one of the scales is holding less weight, one of the scales is holding more weight, but together they're going to add up to that same 10 pound of load. Here are two people on a teeter-totter, and the sum of their moments are 80 pounds times 6 feet, that's force times distance. Here's a negative moment, negative 80 times 6 feet, and that adds up to 0. Remembering that this one that's counterclockwise is positive moment, and this one that's clockwise is negative moment. So you can run the math and find out that yes, they add up to 0. Now, how big is the reaction under here? Well, you can look at it and go, hey, it's 160 pounds. There's two 80-pound people. But you could figure it out with an equilibrium equation. You've got 80 pounds going down, a reaction going up, another 80 pounds going down, and that adds up to 0. So 80 and 80 is 160 pounds going down, a reaction going up, that adds up to 0. Add 160 to both sides, and the 160s cancel out, and you are left with the reaction equals 160. So that's how much that holding up force is. Here's another one, a bigger person on one end, closer to the pivot point. And again, you can add in the force times distance, they add up to 0, remembering the positive moment and the negative moment. So calculate the numbers again. Yep, they add up to 0. Now, how big is this reaction? Well, the sum of all forces in the y direction add up to 0. We've got 80 pounds coming down. We've got a reaction pushing up. We've got 160 pounds coming down, and they add up to 0. So running the numbers together, minus 80 minus 160 is minus 240, plus the reaction adds up to 0. We can add 240 to each side. Those 240s cancel out, and we are left with the reaction equals 240. So that is the size of the reaction pushing up. There you go. Equilibrium, Part 1.